The rest of Unit 3 forces, to me, has everything to do with 3 different predominant situations in which your normal force does not equal your force of gravity. For example, we have an elevator problem. We'll experience a lot of elevator problems. Elevator problems sound more difficult than they really are. You go to build your free body diagram and everything looks to be nominally good, except for, okay, if the elevator's accelerating upward, or if the elevator's accelerating downward, or if the elevator is either moving at a constant velocity or standing still. What's the deal with your normal force and your force of gravity? Well, if our acceleration is directed upward, think of you've just gotten into that elevator and you've just pushed the floor above you and it's just begun its acceleration upward. What's going on with your free body diagram? Well, when you solve for everything, the thing to remember is that your normal force in that case is bigger. It needs to be, because you are now experiencing an acceleration upward. Your force of gravity is now smaller. Just keep that in mind. In that case, when you go to figure out what your net force is still equal to force of gravity plus normal force. It's just that those numbers are changed now. They're not equal to one another. You're accelerating upward. Your net force is no longer 0. Similarly, if you're accelerating downward, if you experience a downward acceleration, then that means that your normal force is smaller. Your force of gravity is bigger. And keep that in mind as you go to figure out your net force. Same rules still apply, it's just those numbers are changed because you're now experiencing a downward acceleration. The other 2 instances of elevator motion are whether the elevator is moving at a constant velocity, or if the elevator is standing perfectly still. If either of these are happening, then your net acceleration and therefore net force are 0. You're not accelerating. We're obeying Newton's first law of motion. In that case, law of inertia. Your net force would be equal to 0. The next type of problem that we would come across is, I guess, what I would term blocks being pulled or pushed at awkward angles. It would seem that your normal force would be equal to your force of gravity. Let's say that we have a rope tied to a block and we're pulling it with a force that's argued in an awkward direction. You know where this is headed. We'll probably be given some sort of reference angle that we can then use trig to figure out what our components of pull force are. In this case, let's say that we're pulling a rope with a pull force of just Fp, pull force. You can already start to see where the trig is headed on that. The pull force in the x direction equal to cosine theta times Fp. In the y direction, sine theta times Fp. And if you don't feel like applying that in every single problem and situation, these mostly hold truth for most problems, so you can just go ahead and memorize those terms. So when you're being pulled up, your net forces are equal to 0 in the vertical direction. That is to say, if I have a rope attached to a boulder and I pull it upwards, the boulder's not going to fly in the air. It's still going to stay tethered to the ground. It will probably experience some sort of horizontal motion, perhaps with friction or those sorts of things going on. But let's not get into that. The net force in the vertical direction, net force, just vertically speaking, is 0. Which is to say that 0 is equal to, okay, hold on to your horses here, force of gravity minus force of normal minus force of pull in the y direction. As in to say that what we're explaining here, or just kind of describing, is that your pull force in the y direction, this vector here, and your normal force, this vector here, when added together, should be equal to your force of gravity, this vector here. Conversely, if we push on a block at an awkward angle, we would have a push force as described above, and then with trig components that we've solved for before. F push in the x direction is equal to cosine theta times F push. Force push in the y direction is equal to sine theta. Cool. Same thing as before. Now when we go to sum up our forces, the only difference now, our net force, once again, we're pushing on the block, so all of your vertical forces have to be equal to 0. All of the vertical forces equals 0. That is to say that this block doesn't get run into the ground or fly up in the air or anything like that. So when you go to sum up your forces in the vertical direction, we know that they sum up to be 0. Therefore, 0 is equal to, okay, here we go, normal force minus force of gravity minus F push in the y direction. Okay, in this case, your force of gravity and your F push in the y direction have to be equal to your normal force. The vector arrows aren't drawn well in this diagram. As far as representative of that, I suppose this normal force should be big in order to describe what would be going on. As a result of that, by the way, when you solve for that normal force, this has all sorts of ramifications with regard to friction. Because the normal force is such an exaggerated number in this situation, this box is now being harder to push. Because as a result of that, we remember force of friction is equal to normal force times coefficient of kinetic friction. Because this number is so much bigger, now this number is going to be so much bigger. This is going to be a harder box to push. Finally, blocks on inclined planes. Blocks on inclined planes are really popular problems in the third and final way in which your normal force is not equal to your force of gravity. Treating it as the same problems as before, your force of gravity is exerted straight down. Gravity doesn't care that you're on a little measly inclined plane because you're on Earth, and Earth is going to pull you perpendicularly downward. Now, you do have a normal force that's exerted here. Normal force. Well, technically, I guess would be between your point of contact with your inclined plane that way. Now, that one is perpendicularly directed such that you get a right angle generated there if we had a force going parallel to the inclined plane. That normal force, and this is a really important, I think this is the first time that we've seen this year, that normal force vector can be picked up off of the page and placed here to build a reference right triangle, not drawn very well, mind you, right there, such that this should be a perpendicular line or a perpendicular point of contact right here. If you notice, you now have a reference right triangle where we have a normal force and a force of gravity. Now that force of gravity is also applied down the inclined plane here. I term this force vector F-gap, or force of gravity, which is applied down the inclined plane. There's a reference angle here of theta. Now that has something to do with this reference angle over here. I'm going to call theta naught. Now theta naught, due to some trigonomic magic, can also be placed here. And you can use that as your reference angle for the rest of the problem. And in fact, a lot of students do use that one. I've routinely used this one as my reference angle for the rest of the problem. Let's go ahead and work this problem with this as our reference angle right here. If we use this angle as our reference angle, it's going to be 90 minus theta naught. And I guess what we can memorize is that the normal force exerted here, using trig rules, we can come up with some trigonomic expressions describing everything that's going on. For example, using angle theta, not theta naught, but theta, we can say that sine theta is equal to force normal over force gravity, and solve for a normal force. Our normal force will not be equal to the force of gravity. It'll be equal to its own number. Similarly, cosine theta is equal to force of gravity applied down the inclined plane over force of gravity. Now, if you don't want to use my angle theta and you want to use just theta naught, it's just the reversed. So cosine theta, theta naught, is equal to, there we go, normal force over force of gravity. And sine theta naught is equal to F gap over force of gravity. And once you have these force vectors outlined and diagrammed, the rest of these problems are just kind of additions to this basic outline here. Getting this basic outline is a good step forward for dealing with the rest of these problems. Problems such as a man's pushing a block up a hill, or the block is sliding down the inclined plane and friction's now involved. Things can get as convoluted as they want, but as long as you have this basic outline, you pretty much can do most of these problems moving forward, and we'll do a bunch of them in class.